Yes. Please, sorry for starting a bit late. Let's start now. No, don't worry. Don't worry. Don't worry. Don't stop it. Let me. Yeah, Onafua, are you there?
Yes, sir.
Sorry. I had several meetings and other things cut me off. Please, sorry. I think
All
it
right.
will not repeat. Okay. Hello and welcome. Let's start immediately. Sorry for not starting in time. We are almost 30 minutes late today. I hope it's not going to happen again. So today we are going to be looking at different laws of chemical combination. But before we get into that, I want to start with stoichiometry. So let's start with stoichiometry, then we'll move on to laws of chemical combination. Okay, so stoichiometry is founded on the law of conservation of mass, where the total mass of the reactant equals the total mass of product, leading to the insight that the relations among quantity of reactants and products typically form a ratio of positive integers. Okay, so in stoichiometry, you try to balance the number of with that of the product. That's what stoichiometry does. And stoichiometry is founded on the principle of law of conservation of mass that says that mass of matter is neither created nor destroyed in the course of chemical reaction. So if you have, say, 10 moles coming in as a reactor, as reactants, you're also going to have 10 moles going out as products. So there is always a relationship between the number of products, the mole number of products and the mole number of reactants. So that is the essence of stoichiometry. And that is also the essence of law of conservation of mass. Okay. So this means that if the amounts of separate reactants are known, then the amount of the products can be calculated. So in essence, you can get the amounts of the product from the amount of the reactant. That's the essence of stoichiometry. Balancing of moles in the reactants and moles on the product side. That's the essence. Okay. Now, conversely, if one reactant has a known quantity and the quantity of the product can be empirically determined, then the amount of the other reactants can be calculated. Okay, so we are still saying the same thing. So this can be illustrated from the equation that is given below. So you can see the equation. Let me check. Okay, the equation says CH4 plus 2O2. So this is simply a hydrocarbon being oxidized to carbon dioxide and water. So you can see that. So there is a balancing of, if you look at, if you check the total number of C on this side, you see that it's equal to the total number of C on this side. Total number of O2 on this side, total number of moles of O2 is also equal to what we have here. And also that of hydrogen. So the number of all these, both on the reactant side and the product side, there is also a relation, there is always a relationship by them being equal. So take note, that is the essence of stoichiometry. And that brings us to the various laws of chemical composition. And you're going to be asked of this law. How this comes out in JAMB is that they are going to state one of these laws and they will ask you, which law is that? So you should be able to tell us whether it's the law of definite proportion or the law of or the law of multiple proportion. You understand? So the first we are going to be looking at is the law of definite proportion, also called the law of constant composition. So this law has, you can call it the law of definite proportion or the law of constant composition. And what does it state? So this law states that all pure samples of the same chemical compound contain the same elements combined in the same proportion by mass. So what do you understand by this law? This law is simply telling you that salt is sodium chloride. So pure sample of salt, sodium chloride in Abuja, and the one that you find in Canada, they must contain the same chemical compound or the same elements. And the elements of salt, which is sodium chloride, is what? Sodium and chlorine. So 1 chlorine, 1 sodium. So whether you get it in Abuja or you get it in Canada, they are always going to contain the same chlorine and sodium in the ratio of 1:1. That's the essence of, that's what this law is saying. Call it constant composition. The composition of chlorine and sodium is always constant, whether you get that chemical in Aba or you get it in Sokoto or you get it in Ogun State. That's the essence of this law. So we call it law of definite proportion. Now, the proportion of combination of chlorine and sodium in sodium chloride, they are definite. It doesn't change, provided you're talking about sodium chloride, pure sodium chloride, except if the sodium chloride is not pure. On that one, I don't know whether this is clear. Did I explain this law clearly? Clear, good.
Yes,
so that's why it's saying that all pure samples of the same chemical, once they are the same chemical, it is sodium chloride, whether it is in Ajegunle or it is in Funtua, they must contain the same chemical elements, the same elements, which is sodium and chlorine, combined in the same proportion. If the ratio is 1:1, it has to be 1:1, whether it's in Bayelsa or anywhere in Nigeria or anywhere in the world that you get it. So that's what this law states. So we call it the law of definite proportion or the law of constant composition. And it states that all pure samples of same chemical compound, contain the same elements combined in the same proportion by mass. Okay. So experiment to verify this law is simply done by analyzing samples of copper oxide, okay? And the method here is to put some white copper triisocarbonate 4, copper 2 triisocarbonate 4 in a dry crucible and heat very strongly. It decomposes, turning from white to black copper 2 oxide and carbon 4 oxide gas is given on. The black copper 2 oxide obtained is dried in this case, okay? These are not as important as the law themselves, okay? So the laws are very, very important because they are what is going to be coming out in your exams. So let's look at the second very important law. And that second law says the law of multiple proportion. You remember we looked at the law of definite proportion or the law of constant composition. So you either call it definite proportion or constant composition. That is the same law. But the second law we are going to be looking at here is the law of multiple proportion. And it states that if two elements A and B combine together to form more than one compound, the several masses of A, which separately combine with fixed mass of B, are in simple ratio. So I want you to be, chemistry is more of a concept. So you have to try in a way to picture the statement in order for you to understand. Now, let's say element A want to combine with element B. So they are supposed to form AB. But in a situation where they don't just form only AB, element A combines with B and is forming AB and is also forming AB2, AB subscript 2. It's also forming AB subscript 3. So when A combines with B, it's not only forming AB alone. So it can produce more than one product. That's what it's saying. That once that is the case, that the ratio which A combines with B in those different compounds are in simple ratio. So let's say for the AB is combining in the ratio 1:1. For the AB2 is combining in the ratio 1:2. For the AB3 is combining in the ratio 1:3. AB subscript 1000 is not possible. So those ratios have to be in simple ratio. So you can always see something like AB1, AB, AB1 or AB2. So it's very, very possible that two different elements will combine together, but they will not form just one compound. It's possible that they can form different compounds depending on the condition of the reaction. Enough one. I don't know whether this one is clear or do I come again?
it's clear, sir.
It's clear, good. So they are very simple but very, very important laws of chemical composition, and we need to know it. So the law of multiple proportion. So take note of the word multiple. Simply means that it is forming more than one compound. That's why they call it multiple. But the proportions of combination are always in simple ratio. So the law states that if two elements A and B combine together to form more than one compound, the several masses of A, which separately combine with the fixed mass of B, are in simple ratio. So if it is AB in one, it might be A2B in the other one, and it might be A3B. So the ratios are always in simple ratio. So experimented to verify there are two porcelain boats labeled A and B. In A is placed some sample of copper 1 oxide, and in B some sample of copper 2 oxide. Weigh each dish again, place the boats into an inclined long hard glass combustion tube, pass hydrogen gas through the tube while the samples are heated. The samples are reduced to reddish brown solid copper, and water condenses at the colder part of the tube. Stop heating, continue passing hydrogen while the tube is allowed to cool. After cooling, remove the boats and weigh each finally. Okay, so just like I said, this is not as important as the law itself. So take note of the law. So finally, we look at the law of conservation of matter. And I told us that this law is just very similar to the stoichiometry. It is based on this very law that stoichiometry is gotten. So this law simply states that matter can neither be created nor destroyed in the course of chemical reaction. I hope this one is clear. This is a pretty very common law in chemistry and in sciences in general. Is it?
Yes, sir.
Okay. So Einstein derived an expression to the interconversion of matter and energy given by E equal to mc squared, or you can call it m. That is actually C, not E. Where C is the velocity of light, and E is the energy, and m is the mass. Okay. So please, this is m. This is C, not E. MC. Okay. MC squared. Okay. So this is the law of relativity. The theory has now been put into law called the law of conservation of matter and law of indestructibility of matter. Okay. So Einstein is actually telling us that matter can actually be converted to energy. So take note, but this initial law of conservation of mass is still a very, very important law. And you're going to be using it in balancing chemical equation, doing a whole lot of things. If you're studying chemical engineering, like me, I studied chemical engineering in the university. So if you're doing plant design, you're going to be doing a whole lot of balancing of masses. So this law is still very, very much used. Okay, so can we recite the three laws of chemical combination? So let's see the people that are around. Let's take it one by one after the other. So let's start with Onafua. Just give me any of the laws, the one you can give us, any of them, any of the three that we just looked at.
Law of conservation of mass.
Okay.
It says that matter can neither be created nor destroyed.
Okay, in the course of chemical reaction. Okay, Stephen, can you help us with one? Stephen, are you there? And I see you raise your hand and I cannot hear you, so I wouldn't know what the problem is. You have a question for us? Okay, so let's move forward with other laws. Let's look at Gay-Lussac's law of combining volume, which states that when gases combine, they do so in volumes which bear a simple ratio to one another when gases combine. So take note of this law. This law is talking about combination of gases, call it Gay-Lussac's law. So whenever they combine, just similar to what law of multiple proportion is also telling us. So, but here we're talking about gases and we're talking about combining volume. So Gay-Lussac's law of combining volume states that when gases combine, they do so in volumes which bear a simple ratio to one another and to the volume of the product if gaseous. if gaseous, provided that the temperature and pressure remains constant. So this law is also a very important law. An example is that experiment has shown that 2 volumes of hydrogen combining with 1 volume of oxygen gives 2 volumes of steam. So you can see the relationship between the volumes that are combining and the volume that is formed. So we have 2 volumes of hydrogen combining with 1 volume of oxygen to produce 2 volumes of steam, not producing like 1,000 volumes of steam. It's not possible. So the volume produced or the mole produced is just similar to what is being combined. So that's the essence of this law. So this Gay-Lussac's law of combining volumes states that when gases combine, they do so in volumes which bear a simple ratio. They have to bear simple ratio to one another and to that of the volume of the product if gaseous, provided that the temperature and pressure remains constant. Okay, so let's look at Avogadro's law. So this law states that equal volumes of all gases under the same temperature and pressure contain the same number of molecules. Equal volumes of all gases under the same temperature and pressure contain the same number of molecules. So what is this Avogadro's law telling us? It's telling us that if 30 cm cube of hydrogen under the temperature of room temperature and normal atmospheric pressure here in Nigeria, and you now get the same hydrogen in the United States of America, but then the temperature there inside the room where it is kept is similar to the temperature that it was in Nigeria here, and the pressure there is also similar to what it had in Nigeria, that it will still contain the same number of molecules. That's what it's telling you. Okay, so by Avogadro's law, volume can be changed to mole when oxygen and hydrogen react as follows. Okay, so this is just the essence of the law. Okay, let's move forward. Okay, so that takes us to chemical symbols. So today, we might, because of the time factor, we might not be looking at past question, but I want us to go far on basic concepts so that we can hit into the main aspects of chemistry, because chemistry is actually bulky. Chemistry is actually bulky. I think more bulk, but more, the volume is more than that of other science subjects, and it could be very, very volatile in understanding. So let's try and drive down a whole lot today. Okay, chemical symbol. Onafua, can you tell me what you understand by chemical symbol? Or can you give me an example of a chemical symbol?
We have SC for scandium, ZN for zinc, O for oxygen, something like that.
Good, yeah. Those are what we call chemical symbols. They're actually abbreviations that you get from their normal name. So these abbreviations could be actually their Greek name or their Roman name. So if you're looking at the normal name, like now you have iron. Can you see the representation? Chemical symbol for iron is Fe, because another name for iron is ferrum. So that's where they got this. So you might not just relate the name of the element exactly to what the symbol is, because the names that we are used might be Latin names. So mostly they use Latin names, but it's actually gotten from the name. So whether it's Latin or the English name, the symbols are always got, like hydrogen H, because you can see it's gotten from this English name of version of the hydrogen. Whereas sodium is Na. Somebody would have said XO, but it's Na. So you need, that's why we study chemical symbols, because you need to know them. And you cannot easily deduce them from the normal English names. And that's why we took out a lecture period to study them. So a chemical symbol is a code. It's actually a code for chemical elements. And you need to know them, because when you're writing your chemical equations, you're not writing hydrogen in full or sodium in full. You have to abbreviate. So when you abbreviate, in order to help you write something that is clearly, you're using chemical symbols. So a chemical symbol is a code for an element. It is usually derived from the name of the element, often in Latin. So take note, those names are often in Latin, that they got them and abbreviated them from. And that's why some of them, they don't have any flat resemblance to the English name that they bear. Okay, this is the example of an atomic symbol. The text boxes explain where the numbers are derived from. For example, okay, so hydrogen is H. That's the chemical symbol of hydrogen is H. Chemical symbol of sodium is Na. Chemical symbol for lead is Pb. Chemical symbol for iron is Fe. Chemical symbol for carbon is C. Potassium is K. Chlorine is Cl. Oxygen is O. And calcium is Ca. Okay, so let's continue. A formula. So from chemical symbol, we come to chemical formula. Okay. Now, the molecules are particles of elements and compounds, and they are represented by chemical formula. So molecules are actually part of elements of compound, and you represent them in chemistry using formulas. And these formulas are simply combining their chemical symbols in the ratio in which they react. So that is what we call formula. So a chemical formula is a sign to represent molecules of elements and compounds, and it comprises of combination of symbols. Just like I had explained, chemical formula is just comprising of symbols. Please, class, can you still hear me?
Yes, sir.
Wow. So why did this thing go? Okay, let me continue. So there are two major formulas that you can have in chemical formula representation. You have what we call the empirical formula and have what we call the molecular formula. The empirical formula is the simplest formula, which shows the simplest ratio of numbers of atoms of element present in a compound. Whereas the molecular formula is the formula which shows the actual number. So the empirical formula shows the simplest ratio, whereas the molecular formula shows the actual number of the atoms of the different elements present in a molecule of a compound, okay? So let's take, for instance, the compound ethyne. The empirical formula is CH. Benzene, the empirical formula is also CH. So you can have up to 10 different compounds having the same empirical formula, because empirical formula is just shows ratio of the different elements combined. For molecular formula, each compound must have its own molecular formula. Okay. So let's move forward. So in the questions that we're going to solve in subsequent class, we're going to be taking detailed way of solving problems involving percentage compositions that we are going to use in solving for empirical formulas and molecular formulas. Okay. So let's move forward. Okay. An equation is a shorthand form of expressing what happens in a chemical reaction. Okay. So every equation must have what we call the reactant part. This is a typical equation. A and B are the reactants, combining in order to form C and D, which are the products. So when a chemical reaction takes place between two or more substances, new substances are obtained, and those new substances are known as products, whereas the substances reacting are known as the reactants. The substances that are undergoing the reactions are called reactants. To write a chemical equation, one must check that the formula of each compound reacting is written correctly. So also is the formula of each of the compounds formed at the end of the reaction. Okay, the reactants are written on the left-hand side, while the products are written on the right-hand side. An arrow is placed in between the reactant and the product, pointing to the direction of the products to show that the reaction is proceeding in the product side. Okay, so this is a typical equation. So in writing equation, make sure you're using chemical symbols to do that. Wonderful. Are we clear on this?
Yes, sir.
Can you still see me?
No, sir.
Okay. I don't know why I cannot see my face. Okay, my video has gone on. Okay, can you see me now?
Yes, sir.
So So let's continue. So these are basic concepts. We are going to solve a whole lot of problems on past questions on what we just did today. So take note of them. That's why I'm moving faster, since we are not solving it now. Okay, definition based on. Okay, let's see what we are. More concept and abbreviations. Okay, kinetic theory of matter, laws, gas laws. Okay, so in subsequent class we are going to be looking at gas laws. We're going to be looking at Charles' law, Boyle's law, and the rest. That's what we're going to be looking at. Charles' law, Boyle's law, Dalton's law, partial pressure. Okay, so we're going to be solving those problems as well. Okay, so I'm going to ask us some questions now before we can round up. So in subsequent class, we are going to be looking at the gas laws. Okay. So Anafo, are you ready for me? Can I ask you some questions?
Yes, sir.
So what are the 3 laws of chemical combination?
Law of conservation of mass or matter,
Okay.
law of constant composition, and law
Okay.
of multiple proportion.
Multiple proportion. Okay. So law of conservation of matter states that matter can neither be created nor destroyed because of chemical reaction. Whereas law of constant composition or definite proportion states that every chemical compound contains the same elements combined in the same proportion by mass. And that of
Yes.
multiple
Multiple.
proposition states that if A and B combine to form more than one product, that the different masses of A that react with separate mass of B are in simple ratio. Are we together on that?
Yes, sir.
You can see I have the 3 of them in my head. You're supposed to also try a way of memorizing them by going through them over and over, okay? Then law of Gay-Lussac's law of combining volume simply states that when gases combine, they do so in volumes which bear simple ratio to one another. And Avogadro's law states that equal volumes of all gases under the same temperature and pressure contain the same number of molecules. So you can have that law stated and you'll be asked which law stated this. So it's you that will pick out and say that this is actually Avogadro's law. This is actually Gay-Lussac law of combining volume or any of the laws. So also take note of the types of formulas that we have. What we call empirical formula, which shows the simplest ratio combination of elements in a molecule, whereas the molecular formula, which shows the actual number of atoms of different elements present. And with that, we'll come to the end of this class. I'll see you when I see you again. Thank you, God bless.